Okay, so recalling the last lecture, as we were finishing up those sets of notes, we talked about these interpolation functions and what will it take to define a set of interpolation functions that give us a unique solution. So ultimately, we want to be able to solve these boundary value problems, get a solution that is unique, right? So that's what we're going to talk about in this set of notes. And to do that, we're going to have to take a step backward and talk about what's called an integral formulation and variational methods. And what this leads to is a natural approach to get these interpolation functions. So what it requires is to think about what's called a weighted integral. Okay, so remember, we want to approximate our true solution based on this nodal set of solutions. We'll show these are the nodal solutions at the finite element nodes. This interpolates in between them. So first off, before we even talk about this function, we need to also get a method to determine these unknown constants. So remember, we talked about variational methods, and we motivated this for a spring. We apply a force on the end, you get a displacement. If you think about internal energy, it's a quadratic function. So it's U equals 1/2 force times displacement, or 1/2 kd squared. So at equilibrium, if you pull on this spring and then you let it go, it's going to go down here, it's going to bounce around. But ultimately, if there's dissipation, or actually if there's no mass, this simply goes to this point. So if you take the variation, you'll show that d actually does equal 0. Now, I also said, what if the force is not 0? Well, what you end up doing is using what's called a Helmholtz energy. And this is a whole other area of thermodynamics using something that's called a Legendre transformation. So basically, we take the internal energy minus the potential, force times displacement, and now we take a variation in this Helmholtz energy and not the internal energy. And what this leads to, again, you take the partial derivative, you get this equation. When it's a minimum, you have the solution. And it's good to see that we get back our original equation. So force equals stiffness times displacement. Alright, so at equilibrium, now you have a non-zero displacement. And I've illustrated that here. You go from force equals 0 to force greater than 0. Here's your solution. So these fairly simple concepts are very powerful in terms of taking this variation in energy. It also defines basically your driving force to go from this point to this point. And you just find where the slope is 0. So it turns out that if you go through this process, and in more complicated problems we'll get into later, if you take the variation in energy, you will get an ordinary differential equation or a set of partial differential equations. Okay, we're going to jump straight to this ODE here. Later we may come back to this, but ultimately the point is there's several different ways to solve these problems. So you want to have a feeling of this concept of variational method, because we're going to use that to set up the finite element problem later. And we're going to make some connections with these ODEs. So let's come back to this ODE that we started to solve last time. We have boundary conditions on both sides. Here we have a displacement on the left side, x equals 0. On the right, x equals L. We've got some flux, or for mechanics, this would be your force. There's several physical examples: cables, bars, heat flow, viscous flow. Electrostatics is governed by this ODE. So what we're going to do is we're going to rewrite the equation in this form, set it equal to 0. We're going to subject these boundary conditions and solve the problem. So again, this problem is very similar to taking a variation in internal energy or Helmholtz energy. You'll get an identical set of ODEs. What I want to focus on right now is consider this equation and then define the whole thing as this function of x. So r is a function of x and their unknown constant Cj at every finite element node. Now, in general, this is not exactly 0. It's only 0 in the true solution. True solution, this is 0, but in finite elements, we are approximating these solutions. Remember, we have this relation. So we want to get this as close to 0 as possible. Okay? So there's several ways to do that. Once you get this close to 0, you have essentially found these solutions, and that means that you have a unique solution for linear problems. Okay? So think about that some more, and we'll come back to that many times. But ultimately, when you solve boundary value problems, you want to drive this to 0. That gives you a solution that is the unique solution, subjected to whatever boundary conditions that you apply to the problem. So there's a number of ways you can do this, and here's what they're called: Petro-Galerkin, Galerkin's method, least squared's method, collocation method. We're primarily going to focus on Galerkin's method. So what that means is you restrict these interpolation functions to be the same as what's called a weight function, right? So there's a subtle difference between the interpolation functions we've talked about, and what I'm going to introduce is a weight function. So what I want to do is make this go to 0 everywhere over the bar from 0 to L. So instead of forcing this to be 0 at every point, I'm going to multiply it by an unknown weight function, and I'm going to integrate over the whole bar. And I'm going to say that only in an integral sense is this problem satisfied. Alright? Again, remember, here is my residual. So it's this ODE, where we've substituted in my displacement. So this is the finite element approximation of our displacements.